My name is Zaris. We are from Group 4. We like to representing material titanium alloy for medical implant and device. This is our group members and they are representing on their part. We have myself for intro and conclusion, Shakir for details on material, Faiz for physical properties of material, Shafiq for mechanical properties and microstructure of material, and we have Saifuddin for method fabrication and application. Introduction of material. Early material used in medical application are like wood, ivory, and bone to make prosthetic limb or and other. Then metal like gold and platinum were commonly used for dental and implant but often rejected by the body. For stainless steel is an alloy that became popular but it is heavy and can cause discomfort for or interfere with mobility. So it was soon discovered the alloy of titanium that have better improved the properties of titanium for medical application.
Next, we move to the detail on the types of material. In this project, titanium alloy were chosen as our material. One of the titanium alloy that is most often utilized in the medical sector, especially for orthopedic and dental implant, is Ti6A aluminum for vanadium. Titanium alloy is composed of 94% of pure titanium, 6% of aluminum, and 4% of vanadium. It is widely used alloy known for its excellent strength to weight ratio, high corrosion resistance, and biocompatibility, making it suitable for various applications including medical and device. The structure of Ti6Al4V can be described at different levels. At the atomic structure, titanium, aluminum, and vanadium atoms form a solid solution in which these elements are uniformly distributed throughout the alloy. The atoms are arranged in crystalline lattice structure, specifically a close-packed hexagonal arrangement known as the alpha phase. When heated up to over 883 Celsius, the atoms begin to rearrange themselves in a different way. At this phase, a body-centered cubic structure or beta phase forms between the titanium atom. We add vanadium in order to stabilize this new phase to maintain it when we cool it back down. Additionally, we add aluminum which stabilizes the new phase and lighten its weight. The titanium alloy now has an advantage of the bimodal microstructure and could resist temperature of up to 350 Celsius since beta phase is more ductile than alpha phase. Given its contain both phases, Ti6Al4V is known as an alpha-beta titanium alloy. In order to create the best material possible, we alter the chemistry, the quantity of each phase, the size of the grains, and even align every single grain of the phase to point in the exact same orientation. As a result, the phase strength, ductility, and the low cycle fatigue characteristics are improved. The beta phase increases the material low cycle fatigue resistance while preventing the formation of fatigue cracks. This combination of modifying phases and heat treating is how we design and develop titanium alloy for use in medical implants and devices.
Assalamualaikum warahmatullahi wabarakatuh. Now I will explain about the physical properties of titanium Ti6Al4V. This titanium is biocompatible, meaning that it can be used in medical implant without causing adverse reaction in the body. This property is critical for medical implant to reduce the risk of infection, inflammation, and other complications. It also promotes tissue integration and reduce chance of rejection. Next physical properties of this titanium is it has high strength to weight ratio, making it an ideal material for medical implant and device that need to be strong and durable but also lightweight. This property is particularly important for implant that need to support the weight of body such as hip and knee replacement. Next, this titanium also is non-magnetic, which make it suitable for medical device such as magnetic resonance imaging MRI machine, where magnetic interference can cause issues. Also, it has excellent corrosion resistance, which is essential for medical implant as they need to withstand harsh conditions of human body without corroding or degrading over time. This titanium also has a low modulus of elasticity, which means that it is less stiff than other materials such as stainless steel. This property is desirable for medical implants that need to mimic the mechanical property of bone and other tissue to reduce stress shielding and promote bone growth. It also has excellent fatigue resistance, meaning that it can withstand repeated loading and unloading without suffering damage or failure. This property is important for medical implants that need to withstand cyclic loading, such as spinal implant or joint replacement.
Moving on to the mechanical properties and microstructure of titanium alloy sheets AL4V, that it may be slightly different based on its processing methods, heat treatment, cooling rates, and other factors. It also has much lower modulus elasticity than stainless steel, which are between 110 to 120 gigapascal, which allow for reduced stress shielding and prevent implant from loosening. So despite having hardness of 36 to 38 HRC, it proved to be quite durable consider its other properties such as having ultimate tensile strength ranges from 936 to 1014 megapascal, which allow for this alloy to support much heavier load without having any deformation. Moreover, this alloy is reputable for its exceptional ductility and malleability that allow for it to be shaped into complex shapes while having low weight to strength ratio and also have better corrosive resistance than steel. So the microstructure of titanium alloy sheets Al4V consists two allotropic crystallographic states, which are alpha phase and beta phase. At room temperature, it occurs as alpha phase, which is a hexagonal closed-packed crystal structure. It transforms into the beta phase, a body-centered cubic structure at around 888 85 degrees Celsius. Lamella microstructure having alternative layers of alpha and beta phase, creating barrier to dislocation movement which allow it to have enhanced resistance to deformation. Next, the martensitic microstructure offer higher adherence of oxide layer to alloy that improve its hardness and corrosion resistance. So lastly is the equates microstructure that offer balanced mechanical properties compared to lamella, multisynthetic, and bimodal, such as balanced combination of ductility, toughness, uniform properties, and biocompatibility that makes this equates microstructure the most suitable for medical application compared to its other microstructure for titanium alloy.
Next, we move to the discussion of fabrication method and application. TI6AL4V can fabricate utilizing a variety of techniques, each of which has advantages and restrictions. Casting, which entails melting the TI6AL4V alloy and putting it into a mold, is one of the most techniques used. Casting can create complicated shape and is relatively affordable, but it has low dimensional precision and can introduce impurities that change the properties of the alloy. TI6AL4V implant and device can also be made by forging, which involve pressing the alloy under pressure to give it the desired shape. Forging allows for the accurate production of several smaller pieces in huge quantities with outstanding mechanical qualities. However, it is somewhat pricey and might be not appropriate for intricate forms. Another popular technique for creating TI6AL4V implant and device is machining, which entails shaping the alloy using drill, lathes, and milling machine. Although machining can produce items with complex shapes and good dimensional precision, it can also be time-consuming and wasteful because a lot of material is removing during process. T16AL4V implant and device are being made via additive manufacturing, often known as 3D printing. Using a computer-controlled laser or electron beam, the part is constructed layer by layer. With great accuracy, additive manufacturing can create items with intricate geometry that are challenging or impossible to do with existing process. Dental implant hip and knee replacement, spinal implant, and cardiovascular device including stent and pacemaker lead are all used for TI-6AL4V implant and device. These implant and gadgets are built to withstand the harsh environment of the body, resist corrosion and wear, and encourage the formation of bone and tissue around them. Due to their safety and effectiveness, TI-6AL4V implant and device are the preferred option for both patient and surgeon.
In conclusion, titanium alloy have revolutionized the medical technology and have significantly improved patient outcome by reducing the risk of implant rejection and improving the longevity and performance of medical implant. With ongoing research and development, titanium alloy are likely to continue to play a significant role, while other materials are used in certain medical implant application. Titanium alloy remain one of the most widely used material due to their unique combination of properties. That's all for our presentation from Group 4. Thank you.